Good morning, everyone, and welcome to the 9th ETP4HPC webinar. I am Pascal, ETP4HPC's Communication Manager, and I will be hosting today's webinar. And my colleague Maria is working behind the scenes. She's taking care of the chat and questions. As usual, this webinar is recorded and you will receive the link on Monday. This webinar is in listen-only mode. Only the speakers are allowed to speak. And also you can use the handout section in the GoToWebinar panel to download today's presentation. Today's presentation is in the handout section. Concerning questions, today we are going to try a new tool. We felt that the questions in GoToWebinar were not really satisfactory, so we wanted a tool so that you can see all the questions asked by other attendees. So we will use Zeetings, like meetings but with a Z. It's very easy to use. You just need an internet browser, and ideally you should use from your smartphone, like I did actually. It's off, but I'm on the site. So you just need to open your browser on your smartphone and go to the Zeetings website, zeetings.com/ETP4HPC to join our conversation. So the URL is shown here, and someone will put it in the chat as well. So in that way, you can see, if you click on the activity bar, you can ask questions, you can see the questions asked by other users. So I repeat, really, I recommend that you use your smartphone. You don't need to download the app. You just need to open your browser, your internet browser, and go to the zeetings.com URL, zeetings.com/ETP4HPC. Now, in Zeetings, questions can be anonymous, but we would really know who is we would really like to know who is asking questions. So we will ask you to enter your name, please. And as I said, Maria will be moderating the questions. If you ask questions about maybe questions about the webinar itself, like if you have a technical problem, she will see it and she will answer immediately. And the questions to the speakers we will keep for the end, and we will ask them at the end. However, we thought if you have a technical problem, if you can't use Zeetings, then you can still ask the question panel, your questions in the question panel in GoToWebinar. It's still possible. So now we have seen all the technical stuff. We'll go to the real focus today, which is MeluXina. We are going to talk about the new EuroHPC supercomputer in Luxembourg, and we have invited 3 speakers, well, 1 moderator and 2 speakers today to talk about MeluXina and give you more insight and information about what they will do with the system and about the system itself. So Hugo Falter will moderate this part, and we will have Valentin Progarou from LuxProvide and Thomas Moshny from Partech. So Hugo, I hand over to you. Are you ready?
Thank you so much, Pascal. I'm ready. So welcome everybody to this MeluXina webinar hosted by ETP4HPC, the European technology platform for high performance computing. My name is Hugo Falter from Partech, and I will be your moderator during this 1-hour webinar. MeluXina. This wonderful name is standing for an outstanding achievement in Europe for high performance computing. It has a history of quite a few years, and it is really with European spirit, with European technology, and set up by European partners in the Grand Duchy of Luxembourg at the LuxProvide hosting site. It all started in 2017 when the research center in Jülich showed its modular system Eureka, which was seen by the representatives in Luxembourg as a raw model, as a solution for their heterogeneous user group, the modular supercomputer shown in Jülich. So we started very early, 4 years ago, to discuss with our friends in Luxembourg a potential setup of the system, and it proved concept that partnership, that co-development, co-design of the system, having the right people from the very early moment, experienced people joining forces, is the way for the success we can now celebrate in Luxembourg. I said it's a European system. It's hosted in Luxembourg. Luxembourg is starting with this hosting site, LuxProvide, their success story of being a supercomputing center. Then the system is designed after an invention by Professor Thomas Lippert, the modular supercomputing architecture, which was together with Partec and other partners in the DEEP project funded by the European Commission, further developed to systems now running in Jülich, running in Luxembourg and other sites to come to really show efficient supercomputing by enabling dynamically access to the different compute nodes and compute processors. So to have a very efficient system with European technology. It was based on 2 steps. Number 1 was the hosting site procurement. This was set up in 2019 by EuroHPC in their first round of procurements. And then it was from LuxProvide side on 15th of April 2019, the application was sent to EuroHPC, finally decided on 4th of June 2019, and Luxembourg became one of the 5 hosting sites for the European petascale systems. This was supported very much by Ina Schmitz as the project management officer of Partec, and Thomas Moschny, the CTO of Partec. You can listen to him in the second half of this webinar. And it was in joint cooperation with the partners and friends in Luxembourg. So the next step was the vendor procurement, which started in August of 2019, and it was awarded in July 2020 to be Atos, the European provider Atos, for the supercomputer MeluXina in Luxembourg. And the continuation of that co-development and co-design aspect started again the project management with Ina Schmitz from Partec. And now we are at the time in the last couple of months with our colleague Jacopo De Amicis, Thomas Moschny, and the colleagues and friends from Atos that the system is ready to go. And this is what we want to highlight today, and highlight also a success story for Luxembourg, Valentin, and it is also a success story for the European technology of modular supercomputing architecture. We call it in short word modularity, and the European cooperation between LuxProvide, Atos, and Partec. Now, let me introduce the speakers to you. And Pascal, if you could go further with the slide, thanks a lot. The first speaker will be Valentin Plougarou. He is the CTO of LuxProvide. And the second one is Thomas Moschny, the CTO of Partec. Valentin, it's your part now.
Thank you very much for the introduction, Hugo. Please allow me to share my screen. I hope this is now visible to you.
Yes, it is. Thank you.
Thank you. Thank you very much for the confirmation. So good morning, everyone. I'm delighted to present you LuxProvide and the MeluXina system today. Our mission of LuxProvide is to provide leading-edge supercomputing and data infrastructure. Actually, the story behind the development of Luxembourg's national supercomputing facilities has quite a history behind. So this has been a greenfield project, one that national stakeholders took part in for several years until it came to fruition. Studies of the national needs, how to answer them, how to integrate supercomputing into key areas, into a data-driven economy. All of this saw concentrated efforts from many partners for years, and the partners were from public administration, academia, and research institutes. During that time, we were pleased to receive the support of the Jülich Supercomputing Center and of Partec, and to become finally a hosting entity for EuroHPC. Our missions are to offer the facilities, but with excellent data and connectivity capabilities. But we are not only doing supercomputing, building and operating these facilities, but also offering competencies and high-level services. They will be done to support projects that can use HPC from people that already know how to use HPC, but also to bring new users into this world. LuxProvide is co-funded by the Luxembourg government and the EuroHPC JU for the MeluXina supercomputer, which is the largest petascale in the EuroHPC network. It will provide 35% of access time to EuroHPC calls, which will be operated shortly, and 65% of the resources will be given to European needs and to national needs. We are located in Bissen, so on the bottom of this slide you can actually see a couple of buildings. The building on the right is the one hosting the main MeluXina system, while the one on the left is a potential expansion. We are located in the Bissen campus, a bit north of Luxembourg City and in the center of Luxembourg. So I think our audience knows supercomputing pretty well, but I will take a moment to reintroduce some key elements on the role of supercomputing. I'm taking a few quotes from the presentation you will find on the EuroHPC website. So the link is on the bottom to see the full details. The impact on transversal role supercomputing has is really shown out through some of these key elements. So to start supercomputing for citizens, actually I will highlight last year, or the year that has just passed, as having seen a truly wondrous effort from the HPC and supercomputing community to bring to bear resources and expertise to help against the coronavirus disease. So HPC has a key role in medicine. It also helps in case of natural disasters, both with a prediction or to support efforts in recovery, and it also supports the efficiency of natural resource utilization and in the fight against cyber attacks, all of which have an impact on people's daily lives. For industry, supercomputing actually helps bring new products faster to market. Time to market is improved for many industries. It can be a key pillar for digital transformation, reducing costs, enabling the development of products and services that were not possible before. The idea is, with the new supercomputers that are being brought up in Europe, to also enable SMEs to use these kind of facilities. In science, well, HPC came out of science, and simulation and modeling were essential for a long time to bring new insights in and deepen our understanding of the world. A few things that are very interesting to see is that some of the recent chemistry and physics Nobel Prizes were using supercomputing as the basis of their efforts. From fundamental physics to material science, earth science, supercomputing really has a very deep and important role to make this possible. Not only happen, but to make it possible at all. As an European context, so EuroHPC joint undertaking was funded some years ago. It started to pilot the provisioning of next generation supercomputers. In late 2019 and 2020, so the new procurements come out of the 8 chosen hosting entities. These sites are now advanced in the implementation of the supercomputers, including the Luxembourg supercomputer MeluXina. So you have likely seen a lot of news coming out of the European Commission, out of EuroHPC, about the development and where supercomputing can help. MeluXina in particular is meant to support both European researchers and industry wherever they are in Europe, and we are very happy in Luxembourg to host also the EuroHPC headquarters. Like I said, we are doing more than just infrastructure, than just supercomputing facilities. We are taking part also in the EuroCC and CASTIEL projects. The EuroCC project in particular is about starting and operating national competence centers. In Luxembourg, this is done with a partnership between Lux Innovation, University of Luxembourg, and Lux Provide. And the idea is that the national competence centers provide this service portfolio that are tailored, of course, to national needs. So each country has one national competence center. And in particular for Luxembourg, Lux Provide is leading work on technology transfer, business development, and collaboration with industry. In this scope, we are going to organize also trainings and workshops to take advantage in particular of the MeluXina supercomputer. To find out more about this, I kept a few links on the bottom. Please check out the EuroCC Luxembourg and our LinkedIn and the Twitter pages. The main topic of today's talk is, of course, MeluXina, which has been built up as a modular supercomputer. So without further ado, I will start to talk about its architecture. The system is built up of several modules. So there are, let's say, 5 main modules in the system. The main computational power comes out of 2 principal modules, the cluster module and the accelerator module. The cluster module is comprised of CPU-only nodes with quite a nice set of computing nodes with a lot of memory on board, and an accelerator module, which is the largest partition, is comprised of CPU, GPU hybrid nodes that are providing actually a lot of the computational power in the system. And there is a smaller partition with FPGA accelerated nodes. So the computational muscle of the system is there. There's also a new separate module for large memory, for in-memory computing needs, which provides a fewer set of nodes, but with high memory available for in-memory workloads. Coupled to the compute is, of course, a storage module, which has HPC storage behind. A tiered storage with different tiers for different needs. And they are all linked together in a high performance network, an InfiniBand fabric, which helps bring out the efficiency of the system. Coupled to this, of course, there's a cloud module that we are designing for high-level services and high-value services, user portals, databases, APIs, orchestration of workflows, and all of it will help users to bring out the true value of the system, not only through HPC simulation and modeling work, but also data-driven workloads that can be piloted from the cloud module. We will have excellent connectivity in the system, so we will have a very nice connections with the GÉANT network piloted through the Restena National Research Education Network provider, and we have also high performance links to partners in Luxembourg through the Luxembourg Internet Exchange, LUXX, and of course public internet access will always be possible. The system is designed as a modular system, like we are mentioning. It's an Atos Bull-Sequana system. So the main computational modules are actually on a DLC solution that I will present a bit in the next slides. and the system is supported by the Partec Parastation Modulo software stack. The building blocks of MeluXina, to start with some numbers, we have around 1600 CPU-oriented HPC-oriented CPUs, 90,000 CPU cores, high-performance cores. They are coupled in the accelerator module with 800 HPC AI accelerators, NVIDIA A100 Ampere generation systems. Altogether, they provide some nice numbers out of them. So there's 5.5 million CUDA cores, 345,000 AI cores. The idea is that different applications can take advantage of this, and we've seen in recent years data science being able to take advantage of these kind of accelerators very, very well. The live memory on the system is over 476 terabytes of RAM. Actually, we don't have an elephant in the system, but elephants are known for their memory, and MeluXina has quite a bit of memory inside. The data storage systems, we have a tiered storage system behind the MeluXina, which couples several tiers plus a long-term archive based on tape technology, whose design decision has been to be able to do 5 petabytes in the beginning, but with the capability to expand to 100 petabytes based on observed needs. Gluing all the CPUs, accelerators, nodes with their memory and the storage together is an InfiniBand HDR interconnect in Dragonfly topology. Many of the nodes in the system are dual rail, so actually you don't have only 200 gigabit per second connectivity, but actually 400 gigabit per second connectivity. This is especially true for the accelerated nodes in the system. And of course, just with hardware, you don't do everything. You need some software on top. We are using EasyBuild as the main tool to deploy software on the system, although we are exploring other options as well, including SPAC. And we are taking a good look at the EC project about how to provide software stacks to users such that they can use and deploy the same tools that they will use on their workstation, from their workstation all the way to the supercomputer environment. While the ones present on the supercomputer environment are of course very, very efficient, and they're compiled specifically for the system, so you're able to get excellent efficiency out of the tools. In terms of raw numbers, if we glue things together, the compute partitions see over 18 petaflops as peak aggregated performance. From the cluster module in the rankings, the system should be ranked as having at least 2.2 petaflops in the HPL known LeanPack benchmark, while the accelerator GPU partition should see at least 10 petaflop or with the same LeanPack accelerated GPU execution. The different modules, again, they're meant to be either all-purpose, like this cluster module, while the GPU, FPGA, large memory are for specialized needs. The FPGA in particular and the large memory should see very specific workloads happening there that will bring true value out of the system, while the cluster and the accelerator GPU parts are much more classical HPC that have already a high level, set of applications being ready to go to use them. The tiered architecture of the storage so comprises these different tiers. The first tier to mention is maybe the scratch tier. So it's half a petabyte. So it's not a true capacity one, but it's very fast. So we hope to see over 400 gigabytes per second in throughput on this data tier. The idea is to have here very highly intensive I/O workloads that take advantage of this. So data science, AI, HPD, data analytics workloads should be really accelerated there. And compared to the total number of nodes in the system, we have a very, very high throughput to the data systems. So data-driven workloads should be really, really fast on the system. Then there is a tier for main capacity tier. This is based on hard drives that has also ultra high performance, not as high as the Scratch tier, but then there's over 12 petabytes of storage there. So it's our main purpose storage tier. Coupled to this are a slower performance tier that's meant for backup from the projects that need this kind of redundancy, and the long-term archival storage that, as I mentioned, can grow from 5 petabytes to 100 petabytes based on user needs. The main interconnect in the system is HDR200. This is in single or dual rail for the internal network. That's excellent. But we also have very high bandwidth networks to the outside, to research, into the research environment, to industry, and to general purpose internet, public internet. The system is maybe very nicely designed from the beginning, because it's hosted also in uptime tier 4 certified data center, the Lux Connect facility in Bissen, which is called the BC2. So this means that there is redundant everything. So there is redundant cooling, redundant power. So the system will be able to sustain high availability services, so to be operated as a production system. The system is in a green data center, which is powered with 100% green energy. And we have the system. The main computational parts of the system are based on DLC, direct liquid cooled technology, which has a very good power usage effectiveness. So that is MeluXina. The vision for the system has always been to serve this large variety of workloads, data-driven computational workloads. Not only pure HPC, but HPDA AI to do data analytics that were not possible before, and to enable simulation that is driven by predictive analytics. And this is now accelerating also classical HPC workloads by simply predicting how things will happen instead of simulating them from the pure equations. So the system, the MeluXina, is built to serve a large variety of workloads and to be highly capable, highly efficient. We hope to see on the system workloads from our Luxembourg's key sectors, so that's smart mobility, health, logistics, space, industry 4.0, fintech, and to have all of this working on this modular system that responds to those needs. To give you some insight on where can MeluXina help in these domains. So if we take space, the analysis of data collected by satellites, that can be really big data. So big data analytics coming from space, data collection from space based satellites, that is one thing. Forecasting space weather, how things look if you want to launch a satellite. That's things that can be predicted and simulated using systems such as MeluXina. Doing material science for space applications, sensors, materials, satellite design, manufacturing and design for zero gravity environments. All those things are possible with supercomputing. In terms of industry, manufacturing, engineering, materials, digital twins has been discussed for quite some time. Virtual testing of prototypes, doing prototyping things and then seeing how they behave versus a real life counterpart. Doing predictive maintenance of parts, exploring how manufacturing systems behave, optimizing product manufacturing. These are things that are helpful in many industries and can help again bring products either faster to market or make it more efficient to bring products to market. In terms of financial services, there's many types of simulations that can take advantage of a supercomputer. Analysis of risk, that's something quite traditional. Fraud and insider dealing detection, this is something that can really be sped up using supercomputers. And things that are very difficult to do, except on a supercomputer environment, such as whole economy simulations, These are things that MeluXina should be able to handle with no issues. More than these fields in mobility, if we think about logistics, route optimization is one thing that can be accelerated with a supercomputer. Virtual testing of automated driving systems, this is something that is now present in many cars, but the work is not yet done. So there's many things that can be improved in the future. Delivery networks, so again, coming back to logistics, traffic management systems to optimize mobility. These things can be accelerated on different kind of supercomputing resources. In terms of healthcare and personalized medicine, digital twins are very important and critical. Developing drug response models before they're actually tested on people. These things are again take a long time to do without a supercomputer, or are not possible to do without a supercomputer. But the next generation supercomputers should really bring up a truly personalized medicine, and this will help in accelerating drug discovery and also testing and doing prediction of life-threatening situations. Climate and weather is a very traditional use case of supercomputers. However, with the new generation supercomputers, we hope to see modeling and forecasting with much higher resolution, doing hyperlocal weather forecasts, to be able to do impact modeling for biodiversity loss, to simulate natural disasters and to plan for response. These things are very much HPC bread and butter. In terms of smart cities, design of smart cities can be done with supercomputers. There's not only the simulation of how things will behave, but also to improve existing environments, and doing whole city simulations and data analytics are very much supercomputers can be used for this. Our value proposition, the modular architecture of MeluXina allows us to answer these kind of needs. So what we will provide is not only these facilities with leading edge platform and low latency interconnect, but also a specialized software ecosystem that enables the large-scale workloads to take advantage of the system. And this, the focus will be on the customers, on our users, with tailored packages, and a dedicated team in the back that can guide throughout the whole process to bring the real solutions to the users. HPC, but HPC, HPDA, high performance data analytics, and AI. We see them using a lot of the GPU accelerators and the large memory systems. Automation of the processes to run on this system will be done through the dedicated cloud module with support. And we hope to help our users design new solutions and to help them discover new business cases for their workloads. What is next for us? In essence, we are opening up MeluXina for users in the coming weeks. We hope to see amazing science and amazing innovation being done with the help of the system. And to leave you with a few images in mind, these are taken a bit from the past months, which were a very exciting time, seeing the development and installation of the system. What you see in the center picture is the face of the MeluXina system, is the direct liquid cooled Bursequana systems that provide the main computational capability of the system. And to the left and right of this picture is the storage tiers of MeluXina under deployment at the time. While on the bottom, you really see on the inside of such a system that is liquid cooled, and that provides, in particular, that's a GPU accelerated node with 2 CPUs and 4 GPU accelerators. With a high connectivity power in the back with the InfiniBand links. The last picture to show is from the first power up, from the first full power up of the system earlier this year, when all the lights were finally up and the system started to be tested. So that was a very exciting time for us earlier. And now we look forward to the system becoming production ready and to onboard the first users. I would like to thank you for your kind attention. I hope I sparked your interest to discover more about us. We are very happy to see your request for information or for any questions that you may have, and to be able to work together to bring a nice usage out of this excellent system. So thank you very much for your kind attention, and looking forward to seeing you in the future.
Thank you, Valentin.
Thank you very much, Valentin. So the next speaker will be Thomas Moschny from Partec in his role of CTO, and will provide information about the contribution of Partec to the system MeluXina. Thomas.
Thank you, Hugo, for the introduction. First of all, I have to apologize that you can see me. That's due to some technical restraints. Anyway, I hope you can see my slides and you can hear me.
We can hear you.
Start.
We can see your slide.
Thank you for the confirmation. Okay, let's start with the first slide. My name is Thomas Moschny. I'm CTO of Partec. Hugo, thank you for the introduction. Well, let's talk a little bit about the history of Partec. Partec was founded more than 20 years ago as a spin-off. It all started as a research project of the University of Karlsruhe in Germany. We consider ourselves an HPC full service provider since 2004. And only 1 year later, in 2005, the ParaStation Consortium was founded. That is based on a strong cooperation with the Jülich Supercomputing Center since 2004. And this cooperation still holds on and is very fruitful. So together with Jülich and other partners, we initiated and heavily contributed to the series of deep projects showing engagement and development in projects towards exascale. And one of the main outcomes of this is the modular supercomputing architecture, which we were pioneering and enabling from the developments in those projects. And since 2017, the ParaStation software is accordingly named ParaStation Modulo. As Hugo already explained, we have been since 2019 a technology partner for LuxProvide in the MeluXina project. Let's move on, please. Just to give you an overview of our technical activities, we have the ParaStation Modulo software suite that I will show you in a few minutes on several slides. It's a software for HPC systems developed for more than 20 years and for more than 10 years pioneering the modular supercomputing architecture. It's not only used in research, but also extensively used in production environments. And MeluXina is obviously one of those. But the software is not the only thing. We also provide service and support. We are engaged with system setup and installation. We help the local teams with system maintenance and administration. We do general first and second level support with our local and remote teams. Besides this, one of the main things we do is co-design and co-development, transferring results from research projects into production is one important goal of that. And the other one is, of course, enhancing production systems over their lifetime. So the idea here is that a system has a certain technology level when it goes into production, but that is continuously being enhanced by some co-development efforts. As I said, we initiated and contributed to the series of deep projects. The latest of those three just finished end of March. The currently going on follow-up projects are the DeepC, IOC, and RedC projects, focusing on various aspects on the way to exascale. So focusing on communication in RedC, focusing on I/O in IOC, and focusing on the programming models in DeepC, and we are part of all of that. We will also be part of the UPEX project, bringing or ensuring that exascale technology is production ready. And we are also contributing to quantum and AI related projects like the HPC QS project and the Center of Excellence RAISE, and the latter of that already started beginning of this year. Next slide, please. So regarding the software, Parastation Modulo, we have three main parts of that. Parastation cluster tools provide tools for provisioning and management. We have Health Checker and Ticket Suite. This is, as we see it, an unparalleled part of our software for automated error detection and error handling, ensuring the integrity of the computing environment. So very important to have a large efficiency of the system, keeping track of issues in the ticket suite, and also bringing analysis tools. And then, of course, we have the Parastation MPI and process management, basically enabling all of that modularity aspects, and that's a runtime environment tuned to the largest distributed memory supercomputers. I will show now in the following slides aspects, those parts of the Parastation Modulo software suite in detail. So the cluster tools basically serve two things. So one is the installation and update of all types of nodes. So we bring, based on an image-based approach, the operating system onto the compute nodes and also onto other nodes. Local modifications are supported. We support multiple images per node. We support things like a rolling update, which is especially important in an environment like MeluXina, where the downtime need to be as low as possible. And we can do synchronization for configuration changes. And that also, of course, includes a boot environment based on PXE. And the second part of that is a set of standard command line interface tools that are used to manage the system. And with those set of tools, we can, of course, do configuration changes. We have our own configuration database to store all the details and all the configuration of the system. We do console redirection and other IPMI functionality, and that is made in a way so that hardware differences that inevitably come when you look at IPMI are hidden behind a uniform interface. And the cluster tools are heavily integrated with the Health Checker and the Ticket Suite, which I will show on the next slide. So the Health Checker, as I said, an unparalleled development of us, is a test framework with generic, fast, and non-destructive tests. And the main idea is to ensure that the system is ready to run a job. And that what is very important here is that it not only covers failing components, but also degraded components. So we can do checks on the hardware, software conditions. We have something like 70 tests, and during installation phases, during configuration phases and deployment of a system, usually the number of tests even increases that we have for the peculiarities of the system. We can do checks on the nodes, so that scales, of course, very well because they are been done locally, and we have a way to do some global checks. For example, to check the state of the system network. So two things here that the Health Checker does. One is when it finds a problem, it disables failing or degraded components and reschedules jobs. so that the system keeps to be usable. And of course, the other thing is that you have to keep track of those problems and ensure that they are fixed eventually. So we create tickets in the ticket suite and send out notifications. Next slide, please. The ParaStation Process Manager is part of the MPI, what we call the MPI. So we have the library and we have the runtime. This slide is about the runtime. It's a scalable network of MPI process management daemons running on the computational nodes, handling all the parallel process startup and control, IO forwarding, and so on, doing resource monitoring, and also ensuring proper cleanup of the jobs. That's also heavily integrated with the health checker, which also ensures after a job that the node is in a good state. And we have the integration, full integration with the batch system and the scheduler by means of plugins to the ParaStation management. So we can totally replace the node local Slurm daemons by the ParaStation daemons, thereby reducing the number of daemons and also enhancing Slurm in various ways. For example, better enforcing resource limits. Next slide, please. So second part of ParaStation MPI is the MPI library itself. It is based on MPICH. However, as you can see on the right-hand side, we replace large parts of MPICH, especially everything beneath the so-called ADI3 interface. This is a layer within MPICH called Abstract Device Interface and allows you to plug in your own driver, basically, and that's what we do. That's powered by PSCOM low-level communication library, which in turn has support for various transports and protocols. So we support InfiniBand, OmniPath, XSOL, which is heavily used in the deep, was heavily used in the deep research projects. And applications may use multiple transports at the same time. That's especially important in a setup where you have multiple transports. Then we are able to bridge transparently between those networks. We provide CUDA awareness for all transports via staging and CUDA optimization via GPU Direct, especially for UCX, which is the InfiniBand transport and XTOL. The MPI library has been proven to scale up to 3,500 nodes and 140,000 processes for a single job. So let's talk a little bit about modularity, and the important thing here is the series of deep projects. We had 3 of them. I already said that. We had deep, deeper, and deepest. In deep, the initial idea was brought into life of a cluster booster system. So meaning you combine a system with a general purpose cluster and a cluster of accelerators, which we call the booster. And you combine them into a single system, having heterogeneity on system level, and allowing applications basically to make use of the parts of that heterogeneous system as they see fit. This idea has then been worked on in deeper, looking on I/O and resiliency, and on deepest in generalizing that idea of a cluster booster concept into the concept of the modular supercomputing architecture, meaning that you could have more than only those 2 types of modules. Co-design was a very important aspect here in those projects. We had all in all, almost 30 partners. That also includes hardware developments, applications, and software developments. Next slide, please. As I said, finally, the modular supercomputing architecture is a generalization of the cluster booster concept. And the idea is that you address diverse user requirements in one system. So could be that an application or a workload is data intensive, or that it needs highly scalable parallel computing, or that it needs high throughput computing. And the idea of those heterogeneity on system level is that you can mix and map your resources and the applications as you see fit. Any number of specialized modules is possible. In deepest, we had a cluster, we had a booster, extreme scale booster, we had a scalable storage module, and we had a data analytics module. So you see the idea of modularity can easily be generalized. And this is, as we strongly believe, the way to achieve leading scalability and energy efficiency on the way to exascale. The important point here is that this is a single system with a unified software environment, and that you are able to run applications across all modules. Next slide, please. Here you can see that in a fancy graphical way. So say you have different applications represented here as those colored blobs, and they make use of the resources provided by different modules as the needs of those applications are. So a data analytics workflow, for example, could use, of course, the data analytics module, the storage, maybe a little bit the cluster, and other workflows would make use of other elements of the module, but they are not limited to a single module. As you can see, they can make use of the resources of any of those modules, and that all in all leads to high efficiency in two directions: for the applications themselves on the one hand, but also for the operator of the system on the other hand, because the resources are used in the most efficient way. And you can see here, if you look at the bottom of that graphic, that of course you could imagine having fancy and new modules which we don't have today, maybe quantum systems or neuromorphic systems. So the modular concept easily allows integrating new modules later. Next slide, please. Yeah, that shows again the development coming from an idea born in Jülich on the left-hand side, where always two types of systems had been installed: the Ukraine system as a highly scalable system, and the Europa system as a general purpose system. And then we had the cluster booster idea realized in deep with the prototype system. But we brought that into production already with the Eureka cluster booster system and further generalized and refined it a little bit in the Joules cluster booster system. Now we have the petascale system in Luxembourg we are talking about today. And that will finally lead us, as we strongly believe, to a modular exascale supercomputer. Next slide, please. Yes, a lot of numbers. I will not go into detail. The cluster booster system, this is just to underline that this idea of cluster booster has already brought into production. You can see here the cluster was already built in 2015. The booster was added in 2017. And that whole system was operated as a single heterogeneous system with power station modulo, and was on number 29 in the top 500 already in 2017. Next slide, please. The cluster which you saw on the left-hand side has recently been replaced by a new cluster, and that's also an important aspect of modularity. You can keep the identity of a system and replace modules with new modules. You can add modules if there's new technology, or you can exchange modules with newer ones after a while, and you keep the identity of the system, and you keep the interfaces for the users, and that's a great advantage in our belief. Next slide, please. Yes, Joules, the modular supercomputer, also a system in Jülich. I don't think we need to go into details here. The booster has recently been installed. And again, this system is also operated as one modular system with Power Station Modulo and the Slurm scheduler. Next slide, please. Yes, and finally, the MeluXina modular system, key element of the data-driven innovation strategy of the Luxembourg Ministry, as Valentin already pointed out, with the splitted budget composed of 6 main modules. The cluster modules with around 2 petaflops peak, the accelerator module based on GPUs mainly with a peak of 10 petaflops, a large memory module, a cloud module, a system module providing access for users, connection to the outside world, and so on, a storage module based on hardware delivered by Atos, the Bullsequana XH2000, liquid cooled, equipped with NVIDIA A100, Mellanox, interconnect, and DDN technology. All the details are in Valentin's slide set, and operated as a modular system with Power Station Modulo. Next slide. I think I'm through. Thank you for your attention.
Thank you. So now it's time for questions. We have received a few. Maria, did you want to share the questions?
Yes, please.
Okay.
Can you see the questions on the screen?
Yes.
Yes.
Okay, so we received 4 so far.
Should we start in order? I think from the bottom.
Yes, and we don't
They are
have
mostly for you, Valentin.
Okay, so I've seen 2 questions that maybe I will answer in a joint way. So there was a question on policy about participation to research innovation projects and how we are going to help SMEs. So while I am not the commercial contact of Lux Provide, so for that I will say that it's a good point to bring up to info@lxp.lu. What I will say is that our mission is to support what people will want to do. So we are trying to bring up expertise to help them use supercomputing and data facilities. So for SMEs in particular, we believe that they will need quite a bit of training and help and dedicated people to help them bring their workflow to a supercomputer and to take advantage of it. So this is something that we will try to do. So we have to see the actual need. Does the SME want to do some data analytics, maybe for an internal project, or is it a project with a partner? These things we need to explore to understand what their needs will be. On the other hand, there was a discussion or the question around financing and other things. So support in finding out how to finance your projects if you want to use supercomputing. This we can explore also with partners, and including it's one of the missions to help from the EuroCC project. So the National Competence Center that is helping you see if there is some funding to take advantage of, such that you can use then the supercomputing facilities and the expertise. So those were the 2 questions received initially. Then there was the question on automation of data workflows. So for the workload manager of the system is Slurm, so that's an HPC workload manager. However, Slurm can be and has been successfully coupled with other orchestration mechanisms. So they can be done. So Containers in particular will be possible on MeluXina through different ways. Singularity containers, which can natively import Docker, that's one thing that will be available day one. However, on the cloud module, if there is some workflow automation tool that needs to be installed for a specific project, again, we will need to understand the needs and to be able to pilot this or the computational modules from that kind of workflow. We really need to see your use case, what you really want to do in a practical terms. So if you have a specific technology in mind, we need to explore how this can be integrated with the system. We are very much in an exploration phase, I would say, for the first months and maybe first year. For the FPGA devices, so on our website there is a technology section which shows the information. I think they're Intel Stratix 10 MX FPGAs with something like 16 gigabytes of high bandwidth memory inside. So they are, well, they're reprogrammable devices, so you can program them to do what you want. They are specifically tailored to HPC and AI workloads, but you can program them in different ways and with different needs in mind. This should support the one API programming interface, such that you don't need to do VHDL, complex VHDL programming. You should be able to use the data C++ to program them.
Thank you.
Thank you. We made it 1 minute last time.
Yes, that's what I was checking. We are right on time. So,
are there any more questions coming up?
No, we
If
haven't
not,
received new questions.
Let me thank everybody, Pascal, Maria, Valentin, Thomas, for hosting and for handling this webinar on MeluXina. And I give back to Pascal to give us maybe more information how we can get access to the videos, etc.
Yes, thank you,
Hugo. Very much.
Thank you to our speakers today. I hope you enjoyed this session. I hope you enjoyed our new Zeetings tool. Now you will receive a survey to fill in at the end of this webinar when you exit the webinar, and it would really help us if you gave us your feedback, especially on this question tool. Our next webinar is on the 18th of June, and it's about the industrial use of HPC, and this time we'll have the standpoints of SMEs. So I have put the link in the chat, but you will also receive it in the email that you receive after the show. So you will receive the link to the recording as well. And well, that's about it, I think. So thanks again to our speakers. Thanks to all of you for attending this webinar, and we hope to see you again on the 18th of June. Thank you. Bye-bye.
Thank you very much.
Thank you. Bye-bye.
Yeah, bye-bye.